The basic tenets of cell theory are that all living things are made up of cells, and that cells are the basic units of life. However, cell theory dives deeper than that. Cell theory has evolved over time and is subject to interpretation. So early cell theory was comprised of 4 statements. The first being, all organisms are made up of cells. And so when I say organisms, that means all living things. Basically, everything that lives is made up of cells. The second part of cell theory was that new cells are formed from pre-existing cells. Part 3, all cells are similar. And finally, cells are the most basic units of life. So in other words, everything is made up of cells. Cells are the basic building blocks of organisms, of life. Now, some other concepts related to classic and modern cell theory include statements such as cells provide the basic units of functionality and structure in living things. Cells are both distinct standalone units and basic building blocks. Energy flow occurs within cells. Cells contain genetic information in the form of DNA. And all cells consist of mostly the same chemicals.
Gene mutations. Gene mutations have several different types. So one would be a missense mutation, which is where one segment of DNA is substituted for another segment of DNA, which tells the gene to make a certain amino acid. And if it's a missense mutation, then it's telling it to make the wrong amino acid. It did code for an amino acid, but the wrong one. And so this could mess up the chain. You could also have a nonsense mutation, where again, a segment of DNA is substituted for the wrong segment of DNA, and it doesn't code for anything. It doesn't code for an amino acid at all, and so the chain ends there. And so it cuts that gene short and could affect the gene function. You also have insertions, which is where a segment of DNA or a base pair is inserted where it doesn't belong, and it alters the arrangement of base pairs, and it could cause the chain to end early, but it's definitely going to change what the chain does, and the function of that gene, that segment of DNA, is going to be changed. You have deletions as well, where a base pair is just deleted, and then most likely the chain is not going to function anymore, and that genetic function is going to fail. So there are different types of genetic mutations. You can have substitutions, where you just have this point substitution, this one area where a segment is changed. You can have insertions, and then you can have deletions. And sometimes this leads to just that one small incident, and sometimes it leads to replication, where there are lots and lots of mutations instead of just the one mutation. Some causes for gene mutation are environmental causes, such as chemicals that you either ingest or that touch your body, radiation, and ultraviolet light, such as from the sun. If you have too much, or sometimes just any amount of some of these things, especially chemicals, any amount of certain chemicals, and then too much radiation or ultraviolet light can make your cells mutate. And it isn't something that happens always, and it isn't something that you can say this will specifically happen, but these are environmental causes linked to gene mutation. Biological causes would be errors made during mitosis and meiosis, and these would be something that certain mutations that might occur in a child whenever the two parents are creating the child. So when that child is forming and mitosis and meiosis are going on, any kind of hereditary mutations are going to be created in that offspring at that time. So you can have environmental causes and biological causes for these gene mutations. And then results of the mutations. Well, the original course of that DNA sequence is altered. So now something else is going to happen. There could be no effect. It could just end. It could not have any effect at all if that DNA chain ends and that function isn't carried out. Maybe it wasn't something very important, and so there's no effect on the organism. It could alter the product of a gene. So the gene's product could come out differently than it was supposed to. Or it could prevent the gene from functioning properly or completely. So maybe the gene's product doesn't get shipped out at all, or it ships out something that it's not supposed to ship out, or it ships out part of something. And the results can be neutral. For instance, a gene mutation in your eye color. You can have brown eyes, blue eyes, green eyes, and the mutation doesn't harm you or benefit you. Generally, it's just going to be a difference, and so it would be a neutral mutation. You can have harmful mutations, such as that causes Down syndrome. You've got an extra chromosome there, and that mutation causes physical and mental problems. And then you can have beneficial mutations, such as that causes sickle cell disease. In the area where sickle cell disease developed, people that had the sickle cell disease were able to fight off malaria better, and so it was a survival benefit to have that mutation. So gene mutations can be caused lots of different ways, and there are lots of different types of mutations, and while most of them have little benefit or harm to us, there are some that can harm or benefit us, but genetic mutation is something that's necessary because it's what keeps people and other organisms evolving and becoming more and more advanced organisms. Binomial nomenclature. Binomial nomenclature is a formal system of naming species of living things. So it helps keep all the different species of living things organized. It's a formal system that is used throughout the world. Each species is given a two-part name based on Latin grammatical form. Though the words can come from other languages, lots of them have Greek roots as well. Now the first part of the name is the genus to which the species belongs, and the second part is the species within the genus. For example, humans belong to the genus Homo and the species Sapiens, so we would be known as Homo sapiens. Note how it is written as well. The whole name is written in italics. Now, this is in normal text. If you were to have the binomial nomenclature, the formal scientific name of a species, in an italicized sentence or italicized paragraph, then you would put just this part, just the scientific name, in Roman typeface to set it off from the rest of the sentence or paragraph. But in normal text, you would italicize the whole scientific name, the genus and species. And it's written in italics with the first part, or the genus, capitalized, and the second part, the species, in lowercase. And so you can see an example for any genus and species. The genus will be capitalized, the species will be lowercase, and the whole thing will be in italics unless there's a situation where the sentence or paragraph is already in italics and you have to set it off from the rest of the sentence or paragraph. And this binomial nomenclature, this two-part naming system, was thought up by Carl Linnaeus, who was a Swedish naturalist, and he formally introduced this system in 1753, and it picked up and it's been around ever since. Think about how many different animals and plants there are. It would be really hard to keep track of all of them throughout the whole world if there wasn't some kind of formal naming system. And since they're based on Latin grammatical form, and a lot of them have Latin roots or Greek roots, the names are going to be the same throughout the world because Latin is a dead language. It's not going to be evolving or changing. and so it's always going to be the same. So if you have a common name for a certain creature or plant in your backyard, and someone else has a different common name for it a couple states over, and someone else has a different name for it in another country, it would be really hard to know that you were all talking about the same plant or animal. But with this two-part naming system, using binomial nomenclature, they're all going to have the same scientific name, and you would be able to say, oh, I have that plant in my yard. Oh, you've got that over in that country? That's neat. I didn't know it was there too. And so all over the world, scientists can communicate with each other and let them know which species they found because they all are using the same formal system of naming. This also omits some confusion with creatures that have the same common name. For instance, a swift can be a lizard, a bird, or a fox. But if you look at the scientific name, the binomial nomenclature, the genus and species of those creatures, you'll see a difference. The fox and the bird and the lizard, even though they can all be called a swift as a common name, are not going to have the same genus or species. So it's going to be very different when you're looking at the scientific name from looking at the common name. So binomial nomenclature is this two-part naming system that helps keep everyone organized and on the same page.
The functions of plant and animal cells vary greatly, and the functions of different cells within a single organism can also be vastly different. So we're going to take a look at plant and animal cells and the similarities and differences between them. And so first, let's take a look at the similarities. Plant and animal cells are both eukaryotic. So they're both eukaryotic as opposed to being prokaryotic. And since they're eukaryotic, they both have a nucleus. And then a third important similarity is their reproduction process. Both plant and animal cells reproduce by duplicating genetic material, separating it, and then dividing it in half. There are also some other similarities related to parts of the cells. They both have cell membranes, cytoplasm, microtubules as part of their cytoskeleton, vacuoles, and then many other structures are the same. Now they both have differences with each other. And so we have plant cells and animal cells. And so one huge difference is that plant cells have a cell wall. Animal cells have no cell wall. And so plant cells have a cell wall made of cellulose that can handle high levels of pressure within the cell, which can occur when liquid enters a plant cell. Now, plant cells have chloroplast. And these chloroplasts come in handy in a process known as photosynthesis. So plant cells have chloroplasts that are used during the process of photosynthesis, which is the conversion of sunlight into food. Chloroplasts in plants that perform photosynthesis absorb sunlight and then convert that into energy. Now, animal cells use something known as mitochondria. And so the mitochondria produce energy from food in animal cells. Another difference is that plant cells have a regular shape. In other words, they pretty much always have the same shape, while animal cells have many shapes. There are many possible shapes that an animal cell could have. And there's also a difference in size. Plant cells are larger than animal cells generally. And then finally, plant cells have cell plates, and so two cells are separated by cell plates, while animal cells pinch in half. So what that means is that plant cells build a cell plate between two new cells, while animal cells make a cleavage furrow and pinch in half. So that's not all the differences between these two types of cells, but these are many of the main differences, and these are many of the main similarities.
Potential and kinetic energy. Potential energy is the amount of energy an object has stored due to its position or orientation. So potential energy is how much energy an object has when it's sitting still. It's just stored. It is not in motion. It's how much energy an object could have if it moved. It's potential energy. And gravity most commonly affects potential energy. Now there are other factors such as mass that can affect potential energy, but the force of gravity on an object is going to affect it the most. So if an object is up higher, it's going to have more potential energy than an object that's down lower, because the lower object is going to have a smaller amount of space to fall. The higher object is going to have a further way to fall, and so it's going to have more potential energy. The formula for finding potential energy, P stands for potential energy, equals mgh. M stands for mass, G stands for acceleration of gravity, so the force that gravity is going to have on that object, and H stands for height. So you'll multiply the mass of the object times the acceleration of gravity times the height from which it is from the ground. And that is going to give you your potential energy. So you can see that the acceleration of gravity and the height, the distance an object is from the ground, are both big parts in this formula for finding potential energy. So gravity is very important to the potential energy in an object. So potential energy is how much energy an object has stored while it's sitting still. Kinetic energy is the energy of an object in motion. So when an object is actually moving, that is whenever you're seeing kinetic energy. And kinetic energy, Ke, can be found with this formula, mv squared divided by 2, where m equals the mass and v equals velocity. So mass times the velocity squared divided by 2 will give you the kinetic energy of an object. So this one doesn't have as much to do with gravity, because once it's in motion, the kinetic energy has more to do with the velocity and the mass of the object. So let's look at this. So we've got this little situation set up. You've built this out of wood or Legos or something, and you've got a ball and you're going to roll it down here. So when your ball is here, you have potential energy. It's sitting still. Once it goes over the edge, and you have it here, you have kinetic energy because this ball is in motion. If it moves down some more and sits still for a minute, you're going to have potential energy as it's sitting still, because it could still go down some more. And if it does, then you have kinetic energy again, because this ball is rolling, it's in motion. And then if it lands here, you've got potential energy again, because it can still drop off this ledge. So potential energy is energy that's stored while an object is still. Kinetic energy is the energy of motion. It's while something is actually moving. So potential is still and stored. Kinetic is moving in motion.
A neutral atom consists of an extremely dense nucleus. And so we see this nucleus right here, and it's going to be composed of one or more positively charged protons. So I'm just going to draw a circle right here and put a P in the middle. So that's going to stand for proton. So this middle circle here represents the nucleus. It's going to be really dense, okay? So it's made up of these positively charged protons. And then inside this nucleus, there's also going to be a varying number of uncharged neutrons. And that exists in every atom except for hydrogen 1. So I'm going to go ahead and draw some more circles. I'm going to put an N in there for neutron. And notice they're connected to the protons. Now there's going to be a cloud of one or more negatively charged electrons outside of the nucleus. And so the number of electrons is going to be equal to the number of protons. So I'm going to draw some circles with an E in them to represent electrons. So we have 3 protons in there. So there's going to be 3 electrons. Now say there's 4 protons, and there's going to be 4 electrons out here. Now there's a bond between the protons and neutrons. They're bound together by a strong nuclear force. And so this force is stronger than the repulsive force between the positively charged protons. So all these protons are positively charged. So I'm going to put a plus symbol. And so positive charges, or like charges, want to repel away from each other. But the bond between the neutrons and the protons are stronger than the repulsive force between the protons. And neutrons, by the way, have no charge. They're not positive or negative. They are uncharged. Now, the negatively charged electrons, which are out here, so these are negatively charged, so I'm going to put negative symbols. So these negatively charged electrons are attracted to the positively charged protons by the electromagnetic force. And so all of these electrons are attracted to the protons that are inside. Now remember earlier I said there has to be the same number of protons as there is electrons. And the reason for that is because this is a neutral atom, meaning it has no charge. And so the 4 positive charges that we have here cancel out the 4 negative charges we have. But say we had 4 positive charges and we had 7 negative charges, then overall this atom would have an overall negative charge. But that's not the case. Because there's the same amount of positive and negative charges, the cell, or the atom as a whole is neutral. Now the number of protons determines the identity of the chemical element, while the number of electrons in the outermost shell determines the ways in which the atom interacts chemically with other atoms or molecules. So this is a shell right here outside the nucleus. Sometimes there are other shells. In this case, there's just one. And so the number of electrons in this outermost shell determines the ways in which the atom interacts chemically with other atoms or molecules. Ionic bonds tend to form under 2 certain criteria. And the first is ionic bonds tend to form between metals and nonmetals. So if you have 2 elements and one's a metal and one's a nonmetal, an ionic bond is likely to form. Now the second criteria is that ionic bonds tend to form between elements with a large difference in electronegativity. So the larger the difference in electronegativity, the better the chance ionic bonds are going to form. And so if elements meet both of these criteria, there's a very good chance they're very likely to form ionic bonds. Now, keep in mind that elements with the highest electronegativity values are in the upper right-hand corner of the periodic table of elements, while those with the lowest are near the lower left-hand corner. So you have elements with low electronegativity down here, and elements with high electronegativity up here. And so just by knowing those 2 facts right there, if you see an element on the periodic table, if you just imagine this board as the periodic table, and it's about right here, you just know by where it's geographically situated on the board that there's a really good chance that it has a high electronegativity because it's near the top right-hand corner of the periodic table. Now, I have some pairs of elements here, and I want to examine these elements to see if they meet this criteria and determine whether or not they are likely to form ionic bonds. So first we have nitrogen and oxygen. Now, nitrogen is a nonmetal, and then oxygen is obviously a nonmetal. So they are not likely to form ionic bonds because there is not between a metal and a nonmetal. We have 2 nonmetals here. Then we have potassium and fluorine. And potassium is an alkali metal. And fluorine is a nonmetal. So we've met the first criteria. We have reaction here between a metal and a nonmetal. So we're doing good so far. And then there's a high electronegativity difference here. And it's actually 3.2, which is pretty high. So they're likely to form ionic bonds, specifically potassium chloride. Now here we have barium and sulfur, and barium is a metal, and then sulfur is a nonmetal. So here we have a metal, a nonmetal. We're doing good so far, so they're likely to form ionic bonds, specifically barium sulfide. And then in addition to that, their electronegativity difference is moderately large at about 1.6. Now finally, we have cesium and tin. And cesium is an alkali metal. And then I'm sure you can guess that tin is a metal. So here we have two metals interacting with each other, so it's not between a metal and a nonmetal. So these cesium and tin is not likely to form ionic bonds. So notice here the main factor here was that we had two nonmetals and two metals here. But when we have a metal and a nonmetal, they're likely to form ionic bonds, and especially if they have a high electronegativity difference. So hopefully through this short session, you have a better understanding of ionic bonds. Nuclear reactions and chemical reactions have many differences, and they have one main similarity. So I'm going to compare and contrast nuclear and chemical reactions. So starting off, nuclear reactions involve the nucleus of an atom. Basically, a nuclear reaction is made up of the composition of the nucleus changing. And so the numbers of protons and or neutrons changes in a nuclear reaction. Now, the electrons are unaffected. So while the nucleus of the atoms going through a nuclear reaction are changing, the electrons orbiting the nucleus remain the same, or the numbers of electrons orbiting the nucleus remain the same. And then finally, nuclear reactions can form different elements. So now we come to chemical reactions. Now, as nuclear reactions involve the nucleus, chemical reactions involve electrons, particularly valence electrons. In chemical reactions, the atoms give, take, and share valence electrons. Now, the nucleus and the rest of the atoms is unaffected. But in particular, the nucleus is unaffected. And I want to drive home that point because up here I talked about how nuclear reactions involve the nucleus, whereas with chemical reactions, the nucleus is unaffected. Instead, it focuses on electrons. But with nuclear reactions, the electrons are unaffected. So we have basically opposite types of reactions going on here, or the way the reactions take place are opposite. And then chemical reactions cannot form new elements, or cannot form elements. But chemical reactions can form compounds. In fact, basically the product of the reaction is compounds. So those are the differences between nuclear and chemical reactions. Now, the main similarity is how they occur. Both nuclear reactions and chemical reactions can occur spontaneously or they can occur with the addition of energy. So as you can see, we have many differences here, but they both come about in the same way, either spontaneously or with the addition of energy. Mechanical advantage is the term used to describe how simple machines make accomplishing work easier. Now, a certain amount of work is required to move an object. And the amount of work cannot be reduced. So how then does mechanical advantage reduce the amount of work you have to do when it says right here the amount of work cannot be reduced? Well, mechanical advantage makes work easier by changing the way work is performed. So say for instance that you need to move an object to a given vertical height. And so a certain amount of work is required to move that object to that vertical height. Now, by getting to that given height at an angle, the effort required is reduced, but the distance that must be traveled to reach the given height is increased. And so although the effort required is reduced, the length of time you have to be pushing or holding that object is increased. And so overall, the amount of work stays the same, but overall it's easier to accomplish that work. So a great example of this is walking up a hill. So say we have a hill right here. If someone wanted to get to the top of this hill, but they're down here, they could take a direct route to the top. So it's going to be very steep, but they don't have to walk very far. But someone else could take a longer route, a meandering route, and go like this. And so as they progress up the hill, they're getting to walk up the hill at an angle. So they're only increasing in elevation slowly, much slower than the person over here who took the direct route. So it requires a lot less effort to walk here because they're not having to gain as much elevation as quickly. But the difference here is that you see how much farther they had to walk than this person because they had to go back and forth. And so even though it was easier to walk up, it took them longer. So the same amount of work is required for both of these. However, mechanical advantage is used right here by the person walking up this hill. It makes it easier overall for that person to walk up the hill. And so there's basically 6 different types of simple machines that use the concept of mechanical advantage. And those are the inclined plane, the lever, the wheel and axle, the pulley, the wedge, and the screw. And so those 6 simple machines use mechanical advantage, and those simple machines can be combined together to gain even more mechanical advantage.
Heat, energy, work, and thermal energy. These are all physics terms, and it's important to know the differences between each of these terms. Heat is the transfer of energy from a body or system as a result of thermal contact. And heat consists of random motion and the vibration of atoms, molecules, and ions. So heat is the transfer of energy based on thermal contact. So 2 things have to touch and energy is transferred based on temperature. Higher temperatures equal more motion. So objects or substances, systems that are heated to a higher temperature are going to have more motion, more vibration in their particles, where lower temperatures are going to have less motion. Heat naturally flows from hotter to colder. If you've got something that is a hot substance and you mix it with a cold substance, the heat is naturally going to flow to the cold until they balance out. But heat can be forced to move from colder substances to hotter substances using a heat pump and or in special laboratory settings. So it is possible to force the heat out of a colder object into a hotter object, but naturally hotter is going to flow to colder. Cold substances have motion, heat. Cold substances have heat, just less than hotter substances. So, for instance, if you have an ice cube and a glass of water, Your glass of water could be cold water. It feels cold to you, but it still has heat in it. If you put that ice cube in the glass of water, the heat from the cold water is going to transfer to the ice cube and start to melt it. So even though it's a cold substance sometimes, whenever you feel it, it actually does still have heat in it that can be transferred. So cold substances have heat, just less than hotter substances. They vibrate, they have motion, just less so than hotter substances. So the cold water is going to be vibrating just less than hot water would. The ice cube is going to be vibrating just less so than the molecules in the cold water. Colder substances have less energy to transfer than hot substances. So if you have a colder substance and a hotter substance, usually that colder substance is going to have less energy to transfer than the hot substance because it's going to have less motion, it's going to have less heat to transfer. So the higher the temperature, the more motion there is, the more energy there is to give away. So now, let's talk about energy. Energy is the capacity to do work, or a measure of how much work can be done by a substance, object, or system. Kinetic energy refers to energy in motion. Potential energy refers to energy at rest. So every substance or object is going to have a potential energy. As it starts to give off that energy, it becomes kinetic, but there's still potential left in there. And if there's some heat source or something giving more energy to the object, it's going to still be gaining kinetic energy, building up potential energy, and giving off kinetic energy. So the energy of a specific object or substance could be changing at a lot of the time. It doesn't just stay stable. It doesn't stay at one specific measurement of how much capacity it has to do work, how much work this specific object could do. So let's think about a boulder going down a hill. So if you have this hill and you've got a boulder, well, it's got potential energy because once it starts rolling, it's going to be giving off kinetic energy. So just sitting there, it has potential. As it starts to go down, it's still going to have potential energy because it hasn't reached the bottom. And then once it does reach the bottom, it might start rolling up the next hill, and then it might roll back. So potential energy is going to continue to remain there. As it's moving, it's giving off kinetic energy. If you had someone else come in and push the boulder, then it would be receiving some more energy and have more than its potential energy would go up, its kinetic energy would go up. So energy is how much work can be done by a substance, object, or system, but it is always changing. So it's hard to nail down that exact capacity because different environmental factors, different physical factors are all going to weigh in on this capacity, this amount of work that could be done. Now let's look at work. So energy is how much work can be done. Work is the quantity of energy transferred. So they are very closely related and they can sometimes be confusing, so it's important to try to work out in your mind what the difference between these two are. So it's the quantity of energy transferred or the amount of energy that must be transferred to overcome a force. For instance, lifting an object in the air, just lifting this marker, requires work. Gravity is the force that must be overcome. Gravity wants this marker to lay flat on the ground. The fact that I'm picking it up requires some amount of work. It requires me to transfer some of my energy to this marker and lift it up. So, work is how much energy was transferred to get this into the air. And work is measured in joules. which is abbreviated with a capital J. The rate at which work is performed is known as power. And this is basically the rate at which energy is transferred. So I have a lot of energy in my body. I have a lot of capacity to do work. When I lift this marker, I am working. I am using a certain amount of work to get this marker in the air. So the quantity that I transfer would be measured in joules, and the rate at which I work is the power at which is my power. It's the rate at which energy is transferred. So I'm transferring energy slowly when I do this, or when I just come up and write. But if I started raising it really quickly, my power would be increased. If I started scribbling out really quickly on the board, my power would be increased. I would be having a greater quantity of energy transferred, and I would be using more of my overall capacity. I would be depleting my energy. Now, if I went and ate some food, drank something, then I would be increasing my capacity to do work again. So that's where energy, the capacity to do work, can be fluid. Work is the amount that's actually transferred to get a job done, and power is how quickly, the rate at which that energy is being transferred. Now let's look at thermal energy, which has more to do with heat, which we talked about before. Thermal energy is the energy present in a system due to temperature. So energy and work and power can all be influenced by a temperature. The total kinetic and potential energy available due to temperature is your thermal energy. So heat is the transfer of energy as a result of thermal contact. Thermal energy is how much energy is available due to temperature. So heat is when energy is transferred due to temperature. Thermal energy is how much is available due to temperature. So it's similar to energy, where it's how much can be done by this object, how much is there. Thermal energy says how much is there due to temperature. And higher temperatures equal more available energy as long as no work has been done. If you heat an object up, then it's going to have more thermal energy. Now, if that object heats itself up, then it's used some work. For instance, if I'm at my normal body temperature, I've got a certain amount of energy available. If I go running, I'm at a higher temperature, but I've used a lot of my energy to raise my temperature, and so I don't actually have more available energy because work has been done. I've worked my body, I have expended energy. Some of my energy is gone now, and so raising my temperature didn't actually give me more energy. But if I were to boil water, I'm doing all the action boiling the water. So the water's energy is, thermal energy is going to increase. It's going to have a higher temperature. It's going to get more energy, more capacity to do work in it as it gets heated. So heat is the transfer of energy based on temperature. Thermal energy is how much energy is available based on temperature. Energy is actually the capacity to do work, how much work can be done with what that object has. And work is how much energy is transferred, or how much energy needs to be transferred to get a job done, where power is the rate at which that work is performed. Mass, weight, volume, density, and specific gravity. These are all important terms that you'll find in physics, and it's important that you know the difference between each one. First, we have mass. Mass is a measure of the amount of substance in an object. So, how many atoms or molecules of that one substance are in a specific object? That's what your mass is. Where weight is a measure of the gravitational pull of Earth on an object. So let's look at our example over here. We have this rectangular prism, and it measures 8 centimeters long, 3 centimeters wide, 5 centimeters high. So its mass, I'm just going to tell you, is 10 grams. Its weight is 1 pound. And in the United States, we measure weight in pounds. Other countries have different units of weight, but pretty much all of the scientific community is going to use grams and the metric system as units for mass. So 10 grams tells us that we've got 10 grams of a substance in this box. The weight says that we have 1 pound of gravitational pull of Earth on that box. Now, this is the gravitational pull of Earth, which means that on different planets or different entities in our solar system, the weight would be different. For instance, on the moon, there is less of a gravitational pull, so your weight would be lower on the moon. On other planets that are further away or closer to the sun, you're going to have a different gravitational pull, so you would weigh more or less on different planets because the pull would be different. But whenever you see a weight listed, it's going to be the gravitational pull of Earth on an object because that's where you are most likely to find these things. Let's move on to volume. Volume is a measure of the amount of space occupied. And there are many formulas to determine volume. It's going to depend on what shape your object is, how you're going to determine its volume. For instance, the volume of a cube is the length of one side cubed, or s cubed, side cubed. And the volume of a rectangular prism is length times width times height, or L times W times H. And in fact, that is the same formula you could use for a cube. One side times one side times one side. Just in a cube, it wouldn't matter which side you picked because they're all the same length. In a rectangular prism, it's important to make sure you take the length of a side times the length of the prism times the width of the prism times the height of the prism. You can't just pick any three sides. The volume of an irregular shape can be determined by how much water it displaces. So say you have a rock and you want to know what the volume of this rock is. How much space does it take up? Well, most of the time a rock is not going to make a perfect sphere, so you can't use that formula. It's not going to make a perfect rectangular prism or cube unless it is formed that way and ground down to be a specific size. Most of the time you're going to find an irregularly shaped rock. So let's look at how water displacement can help us with volume. If you fill a beaker with some water, let's say we start with 20 milliliters of water. Then we drop our rock into the same beaker, and now our water reads 47.5 milliliters. Well, you didn't add any more water. What you added was the rock. So the difference between the new volume and the old volume is going to be the volume of your irregular object. So our rock that we dropped into the water, we can take our new volume, subtract our old volume, and it's going to tell us the volume of our rock, our irregular object. So the new volume was 47.5 milliliters. The old volume is 20 milliliters. And so we take our new volume of 47.5 minus the old of 20 and get 27.5 milliliters. So that would tell you the volume of this rock. And there are different units of volume as well. It is not always given in the same units that width and height and length would be given in, but it can be given in more of a liquid measure since we did measure it this way. Now, a milliliter is also the same as a centimeter cubed, so you could at the same time translate that to 27.5 centimeters cubed. But since we did it with water displacement, I'm going to leave it milliliters. Now let's come back to our example and find our volume. So our volume is going to be length times width times height. So let's take those. 8 centimeters long times 3 centimeters wide times 5 centimeters tall. All right, 8 times 3 is 24, and then we have to multiply times 5. 5 times 4 is 20, 5 times 2 is 10, plus 2 is 12, and so we get 120 centimeters cubed. So whenever we multiplied the centimeters out, it turned into centimeters squared and then centimeters cubed. So your answer for volume is going to be given in cubic units, and so this is 120 cubic centimeters, or centimeters cubed. That is our volume of this object. Now let's move on to density. Density is the measure of the amount of mass per unit volume. So they want to know how much substance is there per the space that it makes up. So some things are going to be more dense. Their particles are going to be smashed more closely together in a smaller unit of volume, where some are going to be more spaced out and they're going to be in a bigger unit of volume. So density is going to tell us how much mass there is per volume, per space that an object is taking up. So the formula for density is mass divided by volume, or D equals M divided by V. And it is given in terms of mass per cubic unit, such as grams per cubic centimeter. Grams per cubic centimeter. So let's find the density of our object over here. So we have our mass, which is 10 grams, and we have our volume, which is 120 cubic centimeters. So now we just have to reduce, and what we're going to end up with is being able to cross out these zeros, and we're going to have 1/12 gram per cubic centimeter. And we can turn that into a decimal because that's usually how we like to see things. So I'm going to do the division up here. So we've got 8 times 12 is 96. We've got 4 left over. Twelve goes into 43 times and we get 36. And this is going to keep on repeating. So we've put another 0 and come down, we get 40 again. So it's 0.083 and it's going to repeat. So we're just going to go to 3 units. So our density would equal 0.083 grams per cubic centimeter. Okay, so our object has a density of 0.083 grams per cubic centimeter. That was based on its mass of 10 grams for a volume of 120 cubic centimeters. Next, let's move on to specific gravity. Specific gravity is a measure of the ratio of a substance's density compared to the density of water. So the specific gravity of a substance would be the density of the substance divided by the density of water. Now, the density of water at room temperature is 1.000 grams per cubic centimeter. If you divide anything by 1, it's going to be itself. So as long as you're at room temperature, the specific gravity of an object is basically going to be its density. But as water gets cooler or hotter, its specific gravity is going to change a little bit. And so specific gravity can change based on air pressure, based on temperature, based on any other physical elements that are going on in the area where you're trying to determine specific gravity. So water isn't always going to be 1 gram per centimeter cubed, but at room temperature it will be. And so as long as everything's at room temperature, regular pressure, then you're going to have your specific gravity be basically the same as your density of the substance. Now, if your specific gravity is greater than that of water, so it's greater than 1 gram per centimeter cubed, then your substance is going to sink. It is denser than water, it's going to sink below the water. If your specific gravity is less than water, then your substance will float. It has a specific gravity that's less than water, it is less dense than the water, so it's going to float. For instance, if you put most metal, if you put a penny in water, it's going to sink because it has a higher specific gravity than water. But if you have a piece of wood, it's usually going to float because it's going to have a lower specific gravity than water. If the specific gravity of a substance is 1 or right at 1, then it will be buoyant. So it'll kind of bob around the top of the water. It won't float right above it. It won't sink to the bottom. It'll bob right around the top. So let's look at the specific gravity of our box over here. So we've got our density of the substance, which is 0.083 grams per cubic centimeter. And we have water, which is 1.000 grams per cubic centimeter. So your specific gravity would just be 0.083 grams per centimeter cubed, because at room temperature, water is going to be 1, and dividing by 1 is going to get you the same thing. So would this one, our box here, would it sink or float? Is the specific gravity less than that of water or greater than that of water? It's less than that of water. Less than specific gravity of water. So when it's less than that of water, it's going to float. So let's review all of these terms and make sure we understand the difference. The mass of our box was how much substance was in there. We had 10 grams of a substance in this shape. It weighed 1 pound. That was how much gravitational pull Earth had on the object. Its volume was based on its actual size, how much space it occupied. And it came out to 120 centimeters cubed, and we got that by multiplying length by width by height. Its density was mass divided by volume. So our mass of 10 grams divided by volume of 120 centimeters, and we rounded that to 0.083 grams per centimeter cubed because we were going to keep repeating forever with that 3. And then the specific gravity was just 0.083 grams per cubic centimeter as well, because at room temperature, water is 1 gram per centimeter cubed as well, and the density isn't going to change very much, so the specific gravity is just going to be the same as the density. Since our object's specific gravity was less than that of water, we know that it will float.